Thermodynamics in chemistry is the set of rules that tell us how energy behaves and what changes are possible. It explains why ice melts in your hand, why hot coffee cools down, and why some chemical reactions happen while others don't. It does not tell us how fast something happens. It tells us whether it wants to happen at all. We always start by dividing the world into two parts. The system is the thing we care about, like a reaction in a beaker or an ice cube. The surroundings are everything else. When an ice cube melts in your hand, the ice is the system, and your hand and the air are the surroundings. Energy moves between them. One big source of confusion is heat versus temperature. Temperature tells you how fast particles are moving on average. Heat is energy that flows because of a temperature difference. A bathtub of warm water can contain more heat energy than a cup of boiling water, even though the cup has a higher temperature because the bathtub has many more particles. The first law of thermodynamics is about energy conservation. Energy cannot be created or destroyed, only transferred or changed in form. When you heat water on a stove, chemical energy in the fuel becomes thermal energy in the water. In chemistry, this idea is summarized by the equation delta U equals Q minus W. Delta U is the change in internal energy of the system, Q is heat added to the system, and W is work done by the system. It is just energy bookkeeping. Chemists often talk about enthalpy, delta H, which is the heat absorbed or released at constant pressure, like in most lab experiments. If a reaction releases heat, delta H is negative. That is exothermic, like burning fuel or using a hand warmer. If a reaction absorbs heat, delta H is positive. That's endothermic, like melting ice or an instant cold pack. The second law of thermodynamics explains direction. It introduces entropy, which is about how spread out energy and matter are. A simple way to think about entropy is the number of possible arrangements particles can have. Spreading out is favored. Perfume molecules spreading across a room is an increase in entropy. Hot coffee cooling down is energy spreading into the cooler surroundings. The key rule is that for a natural, spontaneous process, the total entropy of the universe increases. The system can become more ordered if the surroundings become even more disordered. That is why a freezer can make ice. The water becomes more ordered, but the freezer releases heat into the room and uses electricity, increasing entropy overall. To predict whether a process is spontaneous, chemists use Gibbs free energy, delta G. The idea is captured by the equation delta G equals delta H minus T delta S, where T is temperature in Kelvin. Delta G combines heat effects and entropy effects into one decision. If delta G is negative, the process can happen on its own. If delta G is positive, it will not happen unless you supply energy. This explains why some endothermic processes still happen. Ice melting above 0 degrees Celsius absorbs heat, so delta H is positive. But liquid water has much higher entropy than ice, so delta S is positive. At higher temperatures, the entropy term wins, making delta G negative, and melting happens. Finally, thermodynamics is not the same as kinetics. Thermodynamics tells you if a reaction is allowed. Kinetics tells you how fast it happens. Paper burning is thermodynamically favored, but it needs a spark to start. Diamonds are thermodynamically unstable compared to graphite, but they last because the change is extremely slow. Thermodynamics is common sense made precise. Energy moves, spreads out, and follows strict rules. Once you see those rules, everyday chemistry starts to make sense.